Okay, well, let's get started. It's a pleasure to introduce Tom Dean. So Tom was he went to the West Point Military Academy for undergrad, where he studied electrical engineering. After that, he was an officer in the Army, and then he did his PhD at Stanford, also in electrical engineering. His PhD was funded by the Hertz Foundation. And that's through that I met Tom when we were both doing PhDs in the Bay Area at the same time. So his PhD was in kind of information theory, but then afterwards he switched. He went into industry, was working as an engineer at Bose Allen Hamilton. And then a couple of years ago, he started as a research scientist at Breakthrough Energy, where he's been working on contrails, which is what he's going to be telling us about today. And I'm very excited because I've always wondered about what toxic chemicals the government was spraying down on us. So I'm sure that Tom will explain to us exactly how that works right now.
Cool. All right. Yeah. Thanks for the introduction. So I'm going to talk about airplane contrails and what their climate impacts are, which turns out is actually really huge. And I'm going to talk about how we model this and actually how we can mitigate this climate impact. So just to kind of start. What are airplane contrails? So contrail is short for condensation trail. So they're really ice clouds that are left behind in the wake of an aircraft. So as the engines burn fuel, they emit CO2, water vapor, and other particulates, including black carbon, so just soot. And then water droplets will actually condense on this soot and then subsequently freeze into ice. And that's what a contrail is. So in the right conditions, these contrails will actually kind of grow and spread and kind of form cirrus clouds. So cirrus is just a thin ice cloud that's high in the atmosphere. And so this is a video from Imperial College, just showing these persistent contrails growing and spreading embedded in some cirrus. And this is just a satellite image. So all those kind of white streaks are contrails embedded inside of an cirrus. So the conditions for forming contrails are relatively simple to understand, and we've understood them for over 100 years. So the U.S. Air Force initially studied contrails, and so there's this thing called the Schmidt and Appelman criteria, which just says if the air is sufficiently cold and humid, then you'll form some sort of contrail. This thing is fairly easy to quantify, but really you can break contrails down into two parts. So some of them are very short-lived, so you might see them just lasting seconds or maybe a minute or so behind the plane. That just needs, sufficiently cold and moist air. The ones we care about from a climate impact are when the planes are flying through air that is supersaturated with respect to ice. So these are ice supersaturation regions, or ISSR. I might use that acronym again. So if the ice is supersaturated, the atmosphere there's some thermodynamic instability. It's just kind of waiting for something to come along and nucleate this ice cloud forming, which is what these long persistent contrails are. So why do these have a large climate impact? So all clouds scatter, absorb, reflect radiation. Ice clouds particularly are much better at trapping in thermal radiation than the inbound solar radiation. And these can also persist for hours. So you'll have them during the day and during the night. And at night, they're only trapping in heat and not reflecting sunlight off the surface of the Earth. So overall, they tend to have a net warming impact. So this is just kind of showing this pictorially. The picture on the left, this is a false color image, but it's mostly visible light with near infrared light. So this is a depiction of kind of the solar radiation being reflected back. And you can see in the cirrus cloud some of the land features below. And then on the right is the thermal radiation. So this is long wave infrared. This is all heat coming up off the Earth. And it's just much more opaque in that picture, just kind of showing the same thing in pictorial form. So just to kind of put this effect in numbers is actually pretty striking. So the figure on the left is from a paper by David Lee. This is just a survey paper on the climate effects of aviation totally. So effective radiative forcing is just a measure of average energy trapped in the Earth's atmosphere. So the total kind of anthropogenic effective radiative forcing in a year is around 2.7 watts per meter squared. The contribution of aviation on that is about 100 milliwatts per meter squared. And of that, the largest amount of that comes from these contrail cirrus, so something like 50 milliwatts per meter squared, which is roughly 2% of all anthropogenic climate change. And I want to point out two things. Is one that obviously you see the size of those error bars are huge, almost 100%. So I mean, it's actually really cool to be studying something with so much uncertainty. But I mean, there is a lot of impact for, potential impact even on the lower end of this uncertainty. And then also this number, I have CO2 emissions. So this is actually cumulative CO2 emissions over the entire history of aviation is less than 1 year of the impact of contrails. So that is pretty significant. And then the figure on the right is just showing kind of the density of the effect averaged over a year. So the darker the color is just where there's more warming from contrails. And this is almost directly just correlates to where there's the density of flights. So the highest density of flights in the world is over Europe, followed by North America. Okay, so that's just kind of the high level overview of the impacts. I want to talk about how we actually model and get to these numbers. So there's kind of a few phases you can break the contrail life cycle down into and different modeling techniques you'll use for all of them. So the very initial formation, this sort of process of nucleation, happens in a time frame of kind of less than a second. And that's not something that my team works on, but you need these large eddy simulations. These are much more complex fluid dynamic simulations that are capturing kind of the turbulence coming out of the exhaust and how the gas is mixing with the ambient air. What we focus on are these parameterized models, the second one. So this is studying what's happening to the contrail maybe seconds to hours after it's formed. And we're coming up with some sort of estimate of how does a contrail grow? What are the physical properties of the contrail? What sort of heat is it trapping in? And then kind of the bigger picture, and I'll touch on this a little bit. It's again, not saying our group does, but it's something we fund people to do this for us. There are, you're trapping heat in locally in the atmosphere, but then there are other long-term feedbacks. You're affecting the kind of how natural clouds are forming as well. Those are complicated processes, and you need a kind of global climate model, general circulation model, to simulate those fully. So to kind of understand the full climate impact of contrails, you need this full range of modeling. Yeah.
You said you're going to look at parameterized models?
Yeah.
So in the picture above, are you at any particular point, or are you going to evolve through that?
We're more or less starting here and going through here. So I guess it's roughly where this is.
Oh,
yes. Yep. Okay, so this is the primary model that we use. I'm going to break down the components of it, but it's called the Contrail cirrus prediction model. So it's developed by Ulrich Schumann at DLR, who's been studying contrails pretty much his whole life. So there are a number of inputs to the model. We need very specific information about aircraft trajectories. And we need information about how much fuel the plane is burning at every point along that trajectory. So we reconstruct that. We buy trajectory data. We have aircraft performance models, and we estimate the fuel burn. And then you need to combine that with meteorology data to kind of study how these contrails evolve. So one of the main benefits of using this COSIT model is that it is fairly computationally efficient. So the hard part of using it is really just kind of the data engineering of it's just a lot of data, plane data, weather data. But then to simulate a single contrail, like we can do a global simulation of all of aviation within a couple of weeks once we've kind of ordered all the data. So just to kind of break down some of the components of this model, the initial phase that we're modeling is kind of after the initial nucleation has occurred out of the back of the plane. So there's ice crystals just start to nucleate in the exhaust stream. The number of ice crystals is directly proportional to the amount of soot, just the number of soot particles that come out of it. After that initial formation, the ice is pushed down by the wake vortex of the plane. So as the plane flies past, it's pushing air kind of down and out in a very turbulent process. So this is both kind of spreading it out. It's also sinking down, and so it's adiabatically warming. So there's only a certain fraction of the ice crystals actually survive this process, but you end up with just some sort of plume of ice in the atmosphere. So from here, it's modeled just as a Gaussian plume. So this is just a Gaussian concentration of ice that's going to both advect horizontally and vertically. And it's just going to kind of grow through diffusion. And it'll also be kind of affected by wind shear. So you can get these sort of skewed ellipses. If it's more windy on the top of where the contrail is versus the bottom, it will spread out unevenly.
What's a typical concentration?
Great question. Do I know that off the top of my head? I don't know that off the top of my head. Sorry.
Yeah, as another question.
Yeah.
You said, so they are heated up badly.
That's right.
But the temperature is not really lower there. I mean, it's just from the movement. So
That's right.
Don't they recrystallize then?
They can. Yeah, absolutely. Yep.
Because you said that it sounded as if actually not all of the soot particles, but eventually forming condensation or ice.
So it
But
does.
what would they do? They would then.
Yeah, it does depend actually. So actually, it's very close. If it's really, really cold, it can be pretty close to 1-to-1 of every subparticle forming an ice particle, and almost all of those will survive if it's really cold. But it can be lower, closer to maybe like 1 out of 10. Okay, so once we have this kind of, we're tracking the geometry of this plume, we need to understand what's happening to the ice inside of it. So a lot of times these supersaturated regions of air, they form from some sort of updraft process in the atmosphere. So it's either convective lifting or some sort of synoptic, like a front system pushing it up. And so a lot of times they're even still rising, meaning it's getting colder and the relative humidity is also still rising. As long as the relative humidity with respect to ice is above 100%, you're going to keep having crystal growth. So the ice is going to keep growing larger. But there's some complex processes. The ice crystals will, crash into each other, stick together, break up. And then the crystals themselves are actually falling just due to gravity. And so they'll eventually kind of fall out, sediment out of this area of supersaturation. You'll draw down the water budget. And over time, the contrail will eventually evaporate. And so we'll kind of model this process until the contrail has fully evaporated or sublimated. Okay, the last part now, so you can kind of think we have this massive ice and we have an estimate of kind of the size of ice crystals, the number of ice crystals and kind of its geometry, but we still need to get to the radiative properties. And this is kind of where we start to make a lot more assumptions and just kind of parameterize models based on empirical measurements. There are a lot of different shapes of ice crystals that can form. And we have some idea from in situ measurements that have been formed what kind of the percentage of ice crystals we see. All of these ice crystals have different scattering properties, so different wavelengths of light will be scattered at different intensities with these different shapes of crystals. So there's a lot of kind of approximations, but at the end of the day, we get some sort of rough estimate of different wavelengths of light incident on this contrail will be scattered or absorbed or transmitted at different rates. So that all goes into what's called the optical depth, is really just a measurement of how much light is going to pass through at different wavelengths. Once you have, this is temperature warning.
That's the
projection. Okay, so once you have the optical depth, you need to know how much radiation is incident on both the top and the bottom of the contrail, and that's that data we get from the weather models, which are tracking kind of radiative transfer through the atmosphere. So it's a function of the time of day. Is the sun, above the contrail? Are there clouds above or below the contrail? And then what's on the surface of the earth, snow versus desert versus ocean, will all kind of impact the radiative processes. Okay, so putting this together, this is just kind of a visual of an aircraft forming a contrail. So that's the dashed line, and then is the trajectory, it's the dashed line, and then the contrail is this ribbon kind of advecting out. It's kind of growing in width and then dissipating, and the color represents the net kind of, or the instantaneous radiative effect. So blue is more cooling, red is trapping in heat. And so you can just kind of integrate back along the lifetime of the contrail back to kind of the point where that portion of the contrail was formed. And you can say that, flying through this part of the atmosphere caused a warming contrail that trapped in them this much energy. So the idea, one of the intervention methods that I'll talk about is that if you can just kind of deviate from flying and through these waypoints where there was more warming impact, then you could potentially mitigate this warming. Yeah.
So you described your model for how the contrail gets advected.
Yep.
And how it gets wider.
Yep.
Processes. So is this something that can you compare that part of the model to actual observation?
Yeah. That's right.
And does that match pretty well?
Yeah, it's so that is a great question. A lot of these models, these models were initially kind of parameterized and tuned against real observations. And the corpus of like really solid observations is actually like embarrassingly small. So it is fit against maybe tens of contrails. We are kind of working through improving that. It's very easy to get pictures of very young contrails, so maybe ones that are 15, 30 minutes old. You can see the plane forming them, and you can kind of like track them across the camera. It's surprisingly hard to get good quality photos of contrails that are maybe 3 hours old. And you also kind of need to know, you need to know the age, you need to know the plane that formed at its altitude. So it's just, it's a surprisingly hard thing to get a big corpus of validation data for. Okay, and so I mentioned that one of the advantages of this model is that we can do this on a global scale. So this is just a visual of a few hours of simulated contrails over kind of Europe, near Middle East. But you can see the lighter blue are cooling. So as the sun's kind of directly overhead, they have a cooling effect. As the sun sets, they have more of a warming effect. Just makes for neat visuals. But this enables a sort of large scale global measuring of what are these contrail impacts.
Is it passive convection? They're going by?
Yeah, exactly. They're just,
So okay. So you don't need the contrail there at the model.
Yeah, right. Yep. Okay, so I do just want to make one point of what kind of we haven't modeled. So I mentioned that these contrails form, there's energy being trapped in some part of the atmosphere, and then there are these longer term, maybe climate feedbacks that are happening as well. So the modeling that I just explained is really just modeling the instantaneous radiative forcing of the contrail. So this is just how much energy is being trapped directly under the contrail. As you get towards measuring what are kind of the climate impacts that affect us on the surface of the Earth, you need to consider, amongst other things, the effective radiative forcing that takes into account certain short-term feedbacks that the atmosphere goes through. And this can be on the process of hours or maybe a day or slightly longer. So most notably for contrails, there is some very large interplay with natural cloud cover. So these contrails are competing with natural clouds for water vapor. They're going to have different physical properties. It's not something that's really easy to study. You're kind of at the mercy of using these large GCMs or general circulation models. Yeah.
When you say they're competing with these other clouds, are you saying these other clouds also form out of these saturated regions?
That's right. Yep.
So by flying airplanes, we're like making that not happen as much.
Yep, exactly. Yep. And I'll talk about that more a little later, but there are number of ways that natural ice clouds can form. Most natural ice clouds do need some nucleation mechanism. Actually, the most common mechanism is just mineral dust from like deserts getting evected in the Earth. If it does get cold enough, they'll just kind of spontaneously nucleate as well. But we're ultimately modifying this natural process of cloud nucleation by flying the planes through these regions.
Things like meteorites wouldn't have an effect, right?
That'd be pretty small. Yeah. Right. Yeah. You could get some, one-off things, but yeah. Okay. So, I think, one thing you'll see is that as you kind of step through things in the climate space, a lot of times you start making more assumptions and adding kind of a lot more uncertainty. But there are a number of studies that look at kind of what is the effective radiative forcing of contrails. So one fairly recent one is from DLR. Marius Bickel did this study. So they took a climate model and they put a contrail module in there to try to simulate the effects of contrails. It's fairly interesting. I mean, the first time they ran this, they had the kind of air traffic scaling at 100%. So it's just what is air traffic today. And they actually saw no statistical difference in the change of radiative forcing in the Earth. So the net change that they saw was something like 20 milliwatts per meter squared, but it's plus or minus 1,000%. And that's just because that's the natural variation of the radiative forcing of the Earth. So it's something that's hard to measure. So they scaled this up to a factor of 12. They increased the amount of air traffic by a factor of 12, and there they did see a very statistically significant signal. And I'll talk about in the next slide why that is somewhat valid. But the number that they came up with in this study is, I think, around 0.3. There are other studies out there that come up with similar numbers around 0.4. So, I mean, there's multiple ways of looking at this that come up with somewhat similar numbers. But basically, what it's saying for every 10 milliwatts of instantaneous radiative forcing that our models capture, on average, only 3 or 4 of these milliwatts per meter squared of this energy is kind of translating into heating up the Earth.
So in the estimate you had before comparing this effect to the CO2 emissions,
that was effective radiative forcing. Yep.
Okay,
So-
that was effective.
Yep. And I did note that there, although I didn't define the terms. But yeah, ERF is effective radiative forcing.
But now that I know what that is.
Yes. Yep.
Thank you.
Yeah. Okay, so just to give you some very small sense of why this scaling air traffic to a factor of 12 is a somewhat valid way to study this. We did fund a study at Stanford with Ken Caldera, is a pretty prominent atmospheric and planetary scientist. He's been studying climate change through these GCMs for a good 40 years or so. But in general, this process of kind of amplifying the kind of amount of forcing agents in the atmosphere to kind of study the effects is somewhat well accepted. And so even though kind of the Earth is this very nonlinear system, there are a lot of these effects are actually very linear. So the particular study that he did, he was getting at a number of things, but one of the things he did show is that he saw this very linear scaling in effective radiative forcing based on kind of the amount of contrail-like aerosols you're putting into the atmosphere. So it's just one way of seeing that this even though this study had to ramp up air traffic by a factor of 12 to see a change, like yes, there's good reason to believe that. Okay, so hopefully I've convinced you somewhat that this is a fairly significant problem. So I'll talk about ways that we can deal with it and kind of mitigate the effects. So one of the products that our group has developed are these kind of global contrail forecasts. What I described the COSIP model before. So that's based on trajectory of aircraft. So we've developed a different model we call a COSIP grid model that's based on COSIP, but we're basically kind of predicting on average, if a plane were to fly through any point in the atmosphere, what's the contrail impact that it would have by flying through that point. And so this is just kind of a day's worth of data. The darker red means they're more warming. The blue means they're more cooling. So if you have this sort of tool that you can produce kind of in quasi real time as weather forecasts become available, this can be fed to air flight planners. They can ingest this in a layer like the weather, and they can avoid these regions just like they might avoid other weather patterns like turbulence or icing. And so you can come up with some sort of trajectory for a plane to fly in that's somewhat optimal in terms of time, fuel costs, and also climate impacts. So there's a lot of kind of data that shows that this works really well. So to quantify things a little bit, if you were to look at kind of the proportion of flights that have large climate impacts, if you take the kind of worst 2% of flights from a climate impact perspective, and you kind of you avoid these flying through these harmful regions, you'll actually avoid 80% of all contrail energy forcing. So it's a very small number of flights we need to actually intervene in. And a lot of times the intervention is fairly simple. So this is just an example from a paper we are currently drafting, showing if you were to just fly above or below the contrail regions, that can work pretty well. You can also fly around them laterally, which I'll talk about in the next slide. But generally, per flight intervention, you're talking about somewhere between 1 and 5% additional fuel burn. And so if you average this across the entire fleet, it's a very, very small percentage of extra fuel you need to burn to actually avoid forming these contrails. So we've also worked with a flight planning company. Flight Keys is an Austrian company that actually builds the software that pilots use to plan, airlines use to plan the flights. We took 2 weeks of real data from real airlines, and we looked at what would happen if we did avoid these harmful contrail forming regions. So we did this both with commercial aviation. We took American Airlines flights. We also did this with business jets, and actually business jets tend to fly a little higher, just their trajectories look a little different. So we wanted to, show that this works in both cases. And the numbers we came up with are really, really striking and impressive. So the total increased fuel cost, the total increased fuel burn was 0.07%. The total increased operational cost was tiny, 0.03%. We were able to avoid almost 90% of the contrail impact. So if you were to convert this kind of into dollars spent versus tons of CO2 equivalent in terms of warming impact, the number you get is 60 cents per ton of CO2 equivalent. To put that in a context, kind of estimates of what the social costs of a ton of CO2 is something like $60 per ton. So this is a factor of 100 cheaper. So that sounds really great. There's a couple asterisks that should be put on here. One is that these rerouted flights, they comply with kind of all rules that planes need to follow if they're flying through structured airspace, but this is still being done kind of on a flight by flight basis. So the way that you plan flights in practice is the airline will file, this is just considering my plane and nothing else, this is the optimal route to fly. They send that to air traffic control, and they'll look at, can you actually fly this route because of airspace congestion, et cetera. So I mean, it's certainly possible you could have some effects of like, we're pushing all these planes into some narrow airspace that's highly congested. But even we can spare to lose an entire order of magnitude here, and this is still a really good outcome.
Excuse me.
Yeah.
So for the VistaJet.
Yep.
The EF, I forget
Yep.
what that was, but
Yeah.
it's -100.
Yeah, so we flipped to cooling.
Okay,
Yep, exactly. We eliminated all the warming and they're still flying. We're just ignoring the cooling regions, and it ended up being having a net cooling effect. Yeah.
so can I think of contrails as being like a geoengineering that we can artificially
Right.
cool?
So I will talk about that a little bit at the end. Some people do say that like we can do that. If you actually look at kind of the total cumulative impact, the kind of areas, actually you can see it a little bit in this picture, but the number of like cooling contrails that gets formed is much smaller than the number of warming contrails. So if you were to go out of your way to fly through all these cooling regions, you wouldn't have that big of an effect. But I mean, it is possibly measurable. So yeah, I'm not going to advocate for that. But
And why is that? What brings about the asymmetry?
It's really that these clouds are much more effective at trapping in the thermal radiation than the solar radiation. And so you need kind of the strong solar radiation almost directly on top of the cloud to have the effect. Okay, so another thing that we can look at with our modeling tools are what are the effects of adding, what happens if we start changing things in planes, like the types of fuel we burn, the types of engines we use. So if you've flown on a United flight recently, you've probably heard their ads about SAF, sustainable aviation fuel, but this is something that the industry is moving towards adopting. So these are biofuels made from sustainable feedstocks that are supposedly carbon neutral. And they're actually pretty remarkable because they're just a drop-in solution. You can use them in a commercial plane. Right now, you just put in the SAF instead of the regular fuel. Right now, you can only blend up to 50% SAF with a plane, but we want to get to 100%. There's really not too much that's looking like it would block that. It's just, when you're building planes, you look at what happens after, 1,000 hours of having this fuel, and in the line, those are things that still need to be studied. But anyways, these fuels, because they're made of these bio feedstocks, they have slightly different chemical composition. They have lower aromatic compounds in them, and so they actually burn much more cleaner. So they emit less soot, but they also emit more water vapor as a result. So something's going to change with the contrails as a result of moving this biofuel. At the same time, the modern engines that are being fielded are really, really clean. They just burn much more cleanly. The combustion process is clean. And so we've actually seen about an order of magnitude reduction in the amount of soot that comes out of a plane in the past decade or so, which is pretty remarkable. So what this graph is showing is this gray region is kind of current emissions from planes. In these black lines, these are based on field campaigns, so actually flying planes through contrails and measuring. This is the number of nucleated ice crystals per kilogram of fuel, and this is the number of soot particles emitted per kilogram of fuel. The top line is in really cold conditions, and the black line is in warmer conditions. This is just near the threshold where contrails form. But in cold conditions, this is my comment earlier, there's almost a 1-to-1, almost every single soot particle is nucleating an ice crystal. So this is where we are now. If we adopt both these things, we'll end up actually closer to this regime. And you might hope these curves keep going down, but they don't. And so in the warmer regime, what we think is happening, and there's just some kind of floor that we're reaching. That's just some sort of background aerosol process is getting activated in the exhaust, and we're not really going to get below that, and that's fine. What's happening here is a lot less well understood. There are some studies that indicate that there are other pollutants that can become nucleating agents. So one thing is actually lubricating oil comes out of back of engines, and that, if it's cold enough, might be able to sediment ice crystals. The point is there's, the properties of contrails will change by changing these technologies, and we want to understand, what are the second order effects of kind of, it's new engines and fuels. So just to kind of put this a little bit visually, this is from a group we work with. We didn't fund this, but Joel Ponsby's out of Imperial College in London. So this is kind of the standard operating regime. We have the emissions, they're kind of nucleating the initially water and then ice, and those are kind of growing and sedimenting out. So if you're in the low soot regime, so kind of the lower point on the curve, we have fewer condensation nuclei, so we end up with fewer ice crystals. But you have the same amount of humidity in the air, so that means you have fewer but larger ice particles in the contrail. They grow faster, so the contrail ends up being actually optically thicker, but because these are larger crystals, they sediment out faster and they have a shorter lifetime. And then kind of the last case when that curve starts going back up, this is just a depiction of these are kind of the engine oil droplets or whatever other things are being nucleated. We're actually pretty close to this first picture. But this is almost all based on kind of theoretical models, laboratory measurements, not actually in situ measurements. So how does this all shake out is a little bit uncertain. I'm just citing, there's a bunch of literature on this topic, but just to give a few examples, this top one is from a group at MIT, and they actually showed that moving to biofuels will increase the effect of contrail cirrus. So we'll actually end up with more warming by moving to biofuels. But that's not really the consensus, and there's two other studies. So we participated in this last one, but other people predict that moving to these biofuels will actually reduce the contrail impact by 80% just by switching to this fuel. So a lot of uncertainty, a lot that kind of needs to be worked out here. But it's also exciting to be working in, when the problem is you don't know if the sign's positive or negative, it's kind of cool. Okay, so I want to shift gears a little bit, and I'm going to talk about kind of more higher level uncertainty and I'm going to talk a bit more about kind of this nucleation processes of natural ice clouds and how we're kind of possibly changing that and interfering with that, and what are kind of the second or third order effects of what we're doing. And I think, again, with the caveat, there's a lot more uncertainty, a lot more modeling assumptions that are getting made here. Yeah. So anyways, just to talk a little bit about how natural ice clouds form, and I mentioned this briefly already, but there are a number of nucleation mechanisms. So the three that we show on the right here are all what's called heterogeneous nucleation. So essentially, there is something is causing this nucleation to occur. A lot of times it is some sort of soot or aerosol particle that is causing the freezing. So contrails are an example of deposition nucleation, as a process that I described, and this leads to ice clouds. And I'm not going to cover these in detail, but there's other kind of subtypes of this. The other ways that ice clouds can form are homogeneous nucleation. And so this is where you start with liquid droplets that then just directly turn into ice. These all kind of happen at different temperatures and different humidity levels. Just to give some sense of the idea of this deposition nucleation, it depends on what the actual nucleation condensation nuclei is, but it requires somewhere between 100 and 130% relative humidity with respect to ice. This homogeneous nucleation requires something like 160% relative humidity with respect to ice. So it's just much harder to activate. It requires colder, more humid conditions. So our kind of, if you go through, kind of look at IPCC climate reports, what is kind of the state of our understanding of climate science, the kind of biggest sources of uncertainty are these cloud aerosol interactions, and they're also kind of just understanding ice clouds in general. But this is also something that we've gotten a much better understanding of over the past decade or so. So there was this paper written by a group that was published in Science in 2013. This is mostly based on in situ studies of ice clouds. So they flew planes through ice clouds, collected ice crystals, and they found that almost all ice clouds that they sampled, almost everything was nucleated through heterogeneous nucleation. So they actually melted the crystals and kind of they were able to find residue on the inside that suggested heterogeneous nucleation. So this study concluded that homogeneous nucleation in the atmosphere is actually very rare. And this is cited a lot with that conclusion. But actually, there's a paper that came out in 2018 by Ed Griesbreet at Imperial College, and they looked at cloud properties from the top down from space. So they specifically looked at measurements from a single instrument that's has both LiDAR and radar on it. And they're able to look at the properties of the individual particles in the cloud. And actually what they show is that heterogeneous nucleation is a lot more common than what was previously thought. If you're looking at the tops of clouds, these are the coldest parts of the cloud. It's kind of the cleanest part of the cloud. These are also places where planes don't necessarily fly that high. And so kind of these previous in situ studies were biased against kind of seeing these conditions. And this sort of nucleation is especially common where they saw it is downwind of big mountain ranges. So particularly the Ural Mountains, Himalayan mountains, the Rocky Mountains, you have big, strong uplifts from kind of the wind blowing across the mountains. And so these uplifts are happening faster than most places in the atmosphere. You're getting much more cold, humid conditions with cleaner air, causing this homogeneous nucleation. So why does this matter? Kind of like I described with the biofuels piece, changing kind of the nucleation processes will have a big impact on changing the life cycle of a cloud and changing kind of just the overall properties of the cloud. And this gets really tricky and these models are really sensitive. So what this is showing, this graph is showing, this is just a kind of survey paper on properties of these ice clouds. And if you take different background concentrations of condensation nuclei and you make different assumptions about how effective they are, you change kind of the speed of updraft that's forming the cloud, you can get all sorts of different properties of clouds, different life cycles, different radial properties. So it's a lot of sensitivity to these initial conditions. But the thing that's really well accepted and is kind of seen in this blue line is that clouds that are primarily formed through homogeneous nucleation, they have a lot more ice crystals that are a lot smaller and they tend to last a lot longer and they tend to trap in a lot more heat. And this process is so strong that some people have suggested there's a mechanism for geoengineering called cirrus cloud thinning, which says that if you can suppress this homogeneous nucleation, you might end up having a net cooling effect because these are kind of, the worst from a climate perspective. In the context of contrails, there's kind of another really interesting study that was done in 2019 that's just looking at how effective are these soot particles from emitted from airplane engines at nucleating ice clouds. And this is just a laboratory study, so it's not done in situ, but the results are really interesting. But what they show is that if the black carbon was initially formed in a contrail, and that contrail subsequently sublimates, that black carbon is still in the atmosphere. If it gets caught in the uplift, it's really effective at nucleating a new ice cloud. It doesn't need much more than 100% relative humidity, and it'll just freeze again. However, if that particle doesn't actually start out in a contrail, it's extremely ineffective at nuclear a cloud, and you can basically just ignore it as an aerosol. I don't really fully understand the reason why, but this is the study they reported. And so what they did is they had a series of these kind of vacuum chambers where they pumped in something that resembled aircraft exhaust, and they froze it like it was in a contrail. They heated it up, let it melt, and then kind of refroze it. And this is a process they did to kind of simulate that. Okay, so kind of put this together. This is a paper from 2020 by Zoe and Penner that they're studying the radiative forcing of anthropogenic aerosols on the climate, on ice clouds specifically. And this is considering all aerosols from all anthropogenic sources, not just aviation. So aviation is only a subset of this. But they said that if you were to take out all these aerosols, you would actually see, if you take out all these aerosols, you'd see a net warming effect. So they're causing a cooling influence on the Earth that is somewhat on the order of approximately 200 milliwatts per meter squared. So that's about 10%, offsetting maybe 10% of all man-made climate change. That's about 4 times the impact of contrails. But again, this is all anthropogenic aerosols and not just from aviation. This was followed up. So this is all modeling, not based on a kind of real world experiments. This was followed up by a really fascinating paper in 2020 that looked at how did natural ice clouds respond to the COVID lockdown. In April of 2020, we saw a 73% reduction in air traffic. And so it's kind of this is a natural experiment to look at how do cirrus clouds react. And actually what they saw is that there was a net positive effect. So cirrus clouds globally became more warming, which is kind of the opposite of what all our contrail modeling would suggest. And what's really interesting is that they ascribed this to homogeneous nucleation. They were looking at these same sort of sensors that paper that I mentioned previously by Ed Riespreet. So there's more homogeneous nucleation occurring in the atmosphere. And this result was most prominent downwind of the Ural Mountains, which is also downwind of kind of the heaviest density of air traffic. So it kind of, all the pieces kind of fit together with kind of a causal chain. And this paper also suggests that if we were to move to biofuels, we'd actually have this sort of similar warming effect because we'd be removing this black carbon that's effective as a nucleator. So this is just kind of like, there is some uncertainty, there is some doubt, there's reason to proceed with caution. And I think this is also just kind of a good this is a good example of why people suggest you should approach geoengineering with caution, because you might be making, some change that you think is going to have some positive impact, but, there might be some downstream process in the atmosphere that we completely don't understand, and you have the opposite intent of what you want. Okay, so just to kind of summarize, listen to some conclusions. So I listed some confidence ranges here that aren't really scientific, I guess quasi-scientific. This is just kind of what I think the scientific consensus is from, studying the space, reading the literature. But I mean, we know with almost certainty that aviation is emitting CO2. It's about 2% of all CO2 that humans have emitted since the industrial era comes from aviation. We know that this contributes to global warming. There's no question there. I don't want my comments on biofuels to be misconstrued. So we if we want to keep flying planes, we need to do so sustainably. So we need to move to these sustainable fuels. There's really no other choice. And we know that those will kind of offset a lot of this warming caused by CO2 emissions. We know with very high confidence that, or I said high confidence, but these contrail-induced cirrus clouds do cause a warming effect. There's really very little scientific doubt about that. The biggest question is what's the magnitude? These error bars are close to 100%. But kind of to a first order, they're pulling the climate, and the kind of uncertainties come with what are these second, third order effects. We also know that we can't avoid forming contrails. It's not that hard in the scope of climate interventions. It's very cheap. There are some questions that still remain. They're more kind of system engineering questions, maybe humans factors questions of how do we actually get to this and do this. But from a scientific perspective, this seems fairly sound. We think, I said low confidence, but the most likely scenario is that by moving to biofuels, the warming effects of contrails will be reduced. There is some doubt about that. But really, what that means is that this sort of navigational avoidance will either be more or less important depending on how that kind of shakes out. And then kind of, the last point is that to some moderate degree of confidence, we think that this navigational avoidance to contrails is a good idea. It will be a net climate benefit, potentially, the cheapest climate intervention that is out there. But, obviously this is still some work is needed to understand everything that's happening. So that's my talk. I guess pretty good timing, a little bit early, but we have time for questions. So I work on a team of, there are 5 of us, a mix of engineers and scientists. Some of us have a background in atmospheric science, some of us don't. And then we work a lot with other academics as well. So I cited a lot of papers from Imperial College. Roger's name showed up in a lot of citations. So he's was one of Mark Stetler's PhD students, then postdoc, and now research scientist, has just been studying contrails the whole time. And Mark Stetler is a professor at Imperial College, who we work very closely with, who does transportation and environment, has been a big name in contrails. So anyways, that's my talk. So thanks for listening and happy to entertain questions.
Questions?
Yeah, can you give me an idea of whether this microphysics nucleation process is the biggest source of uncertainty on these error bars, or whether it's this large scale GCM context that you're looking at?
That's a good question. It's really more the latter. So this actually this effect that I mentioned in David Lee's paper, he talks about this. And he describes this not as a contrail process, but this is a cloud aerosol interaction. So this, the uncertainty from this goes into an entire different thing. So the uncertainty of the error bar comes from, it's really, this is true in a lot of the climate space, is that it's not necessarily we did this study and based on, these data points, we constructed these error bars. It's more of a meta study level of this paper reported this number, this paper reported this number, and now we have this spread. So some of the sources of uncertainties there just comes from different models say that contrails grow faster, different models account for their interaction with natural clouds differently. So it's more just, I think, accounting and modeling error rather than. Yes.
Is this a jet problem? You went back to the propeller plane.
Yeah.
Would it go away?
It would. Yeah. So turboprops, piston engine planes, dirigibles, right? Then it is, specifically the jet engine is really the.
So it's people wanting to get someplace fast.
That is, right. In theory, if we, adopt these, if we can make biofuel at scale, we can fly sustainably, but that's completely different conversation. But you're right. If we flew on piston planes, then we wouldn't form contrails. But there's other, those are less efficient. Actually piston planes still use lead in their gasoline. So there's
Nobody's trying to improve.
And there are always second order consequences to.
Is the kind of potential negative impact to biofuels unavoidable, or if kind of the next generation of engine design takes into account much more biofuel usage, will that potentially offset those impacts?
That's a really good question. And I think partly we don't fully know the answer to that. But there's a related phenomena too, and this is something that is kind of playing out now that might address this question before we get there in aviation. But there's a question of marine diesel fuels we've removed all the sulfur content from marine diesel fuels. And so previously, these were causing a similar effect to ocean clouds. They were actually making the clouds over the ocean brighter, and that was actually causing a cooling effect. So we've removed that sulfur to make the fuel burn cleaner to stop giving people like asthma and lung cancer. But it's actually caused the oceans to warm up faster. And part of the challenge is like we didn't actually realize this effect was as strong as it was. And so I mean, we're learning a lot about the atmosphere by doing this. And so there are kind of questions of what do we do now? I don't think anybody's going to say we should put the sulfur back in the fuel, but some people have proposed there are some sort of salts that you can add in additives as an additive that wouldn't have these harmful effects that would go back to kind of this cooling that would happen. So maybe you could do something similar with planes flying. But it's unfortunately a little challenging and complicated. So I think it's a good question and partly a non-answer, but people are thinking about that for sure. Yeah.
So I'm a bit disturbed by like your previous slide where where with COVID lockdown, fewer flights that so they're inferring that there was that the planes produced a negative, produced a cooling.
Yep.
And
that's also what's seen here.
Yeah.
Yeah.
So, okay, but at the beginning you said that the heating effect from contrails maybe is even larger than the heating effect from the CO2 emissions.
Yep.
And if this is the same order of magnitude as that, I mean, would that infer that that we should be flying more?
Right.
That the net effect when you include the contrails and the CO2 from flights is net cooling?
Yeah, I mean, this is a really good question. I mean, this is certainly entirely possible that there is a net kind of zero effect of flying. But part of the challenge is the kind of life cycles of these effects. So these aerosols last in the atmosphere for not that long. I mean, maybe hours, maybe up to a year, and they'll eventually precipitate out. CO2 lasts in the atmosphere for 200 years, I think, is a half-life. And so we are seeing a net neutral effect now, but as we keep flying and emitting more CO2, there'll be more CO2 and the same number of aerosols. And so we'll end up in a worse place. And this is all, again, like a reason why a cause for concern in general about these sort of geoengineering solutions is that it'd be one thing if we were kind of at net zero or on our way to net zero, emissions were going down, but they're not. And so if we're relying on things to cool the earth while still pumping out CO2, we're actually making it worse further in the future. Yes.
Just as a quick sidebar to that, what is this study defining as the time, like the duration of lockdown and like what is the duration over what period?
This study was done they looked at a year's worth of satellite data. And they saw this effect, I think it was fairly instantaneous. I'm trying to remember, I read it fairly recently, but it was like, so this sharp reduction of 73% was really only April, May. And then we started, I mean, certainly flight miles didn't get back up to what they were, but it was much higher. And so the effect was most prominent kind of April, May, June. And then it almost went back to normal. But you have to also happening at the same time, there's a number of confounding factors, right? A lot of emissions stopped. And there's also just meteorological variation that makes this hard to, but actually, another interesting point too is that the instrument that they used to measure this no longer operates. And so like I asked somebody we work with, what does this look like now? And he's like, oh, we have no idea what these clouds are doing now because we can't measure it. They are launching a new satellite in about a month that will replace it, but it's not up yet. So, Yes.
In terms of kind of optimizing routes to avoid contrail formation, how much or is there a benefit to kind of optimizing multiple aircraft at once? Do we see nonlinearities in the impact?
Yeah, right. So that's something that I also didn't really cover. Let me go back to show this, but it's something that actually really isn't very well understood is kind of what's the incremental harm or benefit of more aircraft passing through a certain region of the atmosphere. So, I mean, these contrails can kind of grow, they will grow and overlap. They're competing for moisture. And so the effect of kind of 10 planes flying through one region is not 10 times the effect of one plane flying through one region. But that's not something that's actually been very well quantified. And so, I mean, this does kind of come to a kind of collective action problem to some extent, right? If one operator ends up flying through this region, then is there any point in avoiding it? So maybe you need to have some sort of more complex incentive or penalty structure to do this. Jointly optimizing plane trajectories is very hard to do across carriers. And the aviation space is really weird and I mean, it's slow to change, I think, for good reason, but parts of it are just very, their operating margins are low. Like they don't make a lot of money off of flying the planes. And they're really sensitive about like fuel burn data to the point that we'll talk to these airlines and we'll say like, oh, like we'd like to like, you know, get the fuel burn numbers, and they'll say, we can't give those to you, that's sensitive. And they're like, okay, well, we can give you the model and can you run it? And they're like, oh no, like they won't let our data science team see these fuel burn numbers because they're so sensitive. So, I mean, we have our own models that estimate them and they actually get pretty close from what we can tell. But the point is that airlines are just so sensitive about everything. They wouldn't let, you know, somebody jointly optimize two airlines routes. That would like not currently happen without some external incentive. Does that answer your question?
Yeah.
Yeah.
Okay. Straight up, can't do that.
Yeah.
Yeah. Last questions?
Yes.
Yeah, does any of this change if we start flying supersonic?
Yeah, it does. And so actually I mean, assuming you're flying supersonic the way like the Concorde flew and you're flying higher, then you're just flying high enough in the atmosphere that there aren't contrails. So that solves the problem. Yeah. Probably burning a lot more fuel, but there are people at NASA that are studying that actually, contrails of supersonic planes. And it's funny, we talked to NASA. It's an interesting organization in that I don't know if you have experience working at NASA, but they can only get, like, it's very kind of political what they can get funding for. And so like, if we talk to them, they want to study contrails. So like, well, we're really interested in this, but you need to like tag on something else that the administration cares about, like supersonic planes. And then, yeah, so it happens a lot, but. All right.
Okay, well, thanks again. Let's thank Tom.
Yeah, thank you.
One question on
okay,
if you can open up the chat.
Okay. Question on the chat is less efficient aircraft were removed from the fleets, and is there a correlation between more efficient engines during the COVID-related restrictions and increased forcing from aviation contrails? That's a really good question, and I don't think anybody studied it in depth. So I don't have an answer to that. There is a study ongoing right now where people are looking at satellite imageries of contrails and actually trying to match up like this specific engine on this specific plane, trying to make correlations between persistence times and that sort of thing. So yeah, that's something that is being studied right now, but that's the answer for it.
Thanks.